This call is now being recorded.
Good morning, everyone. In last lecture, we have seen unit quantities. In last lecture, we have seen unit quantities. Today, we are going to see unit power under the heading unit quantities. We are going to see unit power. Then what is the definition of unit power? It is defined as power developed by a turbine working under a unit head. That means 1 meter. It is denoted by symbol PU. That is unit power. The expression for the unit power is obtained as follows. H is equal to head on the turbine, then capital P is equal to power developed, then capital Q is equal to discharge. Okay. Then, as we know, the equation for the overall efficiency, is given as power developed divided by water power. Okay. Therefore, overall efficiency is equal to power developed upon water power. Therefore, the equation will become as overall efficiency is equal to P divided by rho G Q H divided by 1000. Rho G Q H divided by 1000. Now we want equation for the power developed. Therefore, P is equal to overall efficiency into rho G Q H divided by 1000. Rho G Q H divided by 1000. This is the equation for the power. Then rho and G and 1000 are constant. Therefore, P is proportional to Q into H. P is proportional to Q into H. But as we know that this Q is proportional to square root of H, therefore P is proportional to square root of H into H. That means P is proportional to H raised to 3 by 2. P is proportional to H raised to 3 by 2. I am introducing here constant of proportionality as K3. Therefore, the equation will become as P is equal to K3 into H raised to 3 by 2. P is equal to K3 into H raised to 3 by 2. Okay. Now, when this power is called as unit power, when our head will become as 1 meter. Okay. Therefore, P is equal to PU, that is equal to K3. Therefore, head is equal to 1. Head is equal to 1. Therefore, constant of proportionality is equal to PU, that is unit power. Now, substituting the value of the constant of proportionality, we will get P is equal to PU into H raised to 3 by 2. P is equal to PU into H raised to 3 by 2. But we want a relation for PU. Therefore, and this is the final equation for the unit power. This is the final equation for unit power. This is final equation for the unit power. Now, in last lecture, we have seen unit speed and unit discharge. In this lecture, we have seen the equation for the unit power. Now, our next term, that is specific speed. Now, we are going to see the equation or the derivation for the specific speed. We are going to see equations for the specific speed. Now again, for equation for specific speed, we are considering the overall efficiency of a turbine, that is equal to overall efficiency is equal to shaft power divided by water power. Okay. Now overall efficiency is equal to shaft power is denoted by P and water power is denoted by rho G Q H divided by 1000. Rho G Q H divided by 1000, where H is equal to head under which the turbine is working, capital Q is equal to discharge through the turbine, and capital P is equal to power developed or the shaft power. Now we want the equation for the power developed. Therefore, power developed is equal to overall efficiency into rho G QH divided by 1000. Rho G QH divided by 1000, where D is the diameter of the actual turbine, capital N is equal to speed of the actual turbine, U is equal to tangential velocity of the turbine, Ns is equal to specific speed of the turbine, capital V is equal to absolute velocity of the turbine. Now, as we know, the absolute velocity, tangential velocity, and the head on the turbine are related as below. That means U is proportional to V. U is proportional to V, where V is proportional to square root of H. Therefore, U is proportional to square root of H. As U is proportional to V, where V is proportional to square root of H, therefore U is proportional to H. Okay. But the tangential velocity U is again given by the equation pi d n divided by 60. It is given by the equation pi d n divided by 60. Now, U is proportional to dn. Our efficiency equation, we will mark it as equation number 1. Then power equation, we will mark it as equation number 2. Then U is proportional to square root of H, we will mark it as equation number 3. These are our 3 equations. Okay. Now U is proportional to dn, we will mark it as equation number 4. We will mark it as equation number 4. Now, from the equation 3, we will write next equation. We will write the next equation. It is square root of h is proportional to dn. Square root of h is proportional to dn. Therefore, d is proportional to square root of h divided by n. Square root of h divided by n. We will mark this equation as equation number 5. Okay. Now, as we know, the discharge through the turbine is given by the equation Q is equal to area into velocity. Okay. Q is equal to area into velocity. Therefore, discharge is equal to area into velocity. But area is proportional to B into D. But area is proportional to B into D, where this B is called as width. And since B is proportional to D, therefore we can write it as area is proportional to D square. Area is proportional to D square. Okay. And velocity is proportional to square root of h. Velocity is proportional to square root of h. Therefore, Q is proportional to d square into square root of h. Q is proportional to d square into square root of h. Now, putting the value of d, that is d is proportional to square root of h divided by n in this equation. Therefore, Q is proportional to square root of h divided by n bracket square into square root of h into square root of h. Therefore, it will become as, now squaring this, Q is proportional to h divided by n square into this square root of h into this square root of h. Therefore, Q is proportional to h raised to 3 by 2 divided by n square. H is proportional to square root of 3 by 2 divided by n square. Now, substituting the value of the Q in equation 2, we will get the equation as P is proportional to h raised to 3 by 2 divided by n square into h. Therefore, P is proportional to h raised to 5 by 2 divided by n square. P is proportional to h raised to 5 by 2 by n square. Now, here I will introduce constant of proportionality, that is K h raised to 5 by 2 divided by n square. H raised to 5 by 2 divided by n square, where K is equal to constant of proportionality, where K is equal to constant of proportionality. Okay, now if P is equal to 1, H is equal to 1, the speed will become as specific speed. Means P is equal to 1, H is that is ns, that is ns. Therefore 1 is equal to 1 k into 1 raised to 5 by 2 divided by ns square, divided by ns square. Therefore k is equal to ns square. We got the value of constant of proportionality, or we can write it as ns square is equal to k. ns square is equal to k. Therefore, p is equal to ns square into h raised to 5 by 2, h raised to 5 by 2 divided by n square, divided by n square. From this equation, we want the value of ns, that is specific speed. Therefore, ns square is equal to n square p divided by h raised to 5 by 4. h raised to 5 by 4. Okay. Now, what we want the value of ns. Therefore, ns is equal to n into square root of p, n into square root of p square root of p divided by h raised to 5 by 4. ns is equal to n into square root of p divided by h raised to 5 by 4. So, this is our final value for the specific speed. This is the derivation for specific speed, that is ns is equal to n into square root of p h raised to 5 by 4. Then what is the significance of our specific speed? What is the significance of our specific speed? Specific speed plays an important role for selecting the type of turbine. Also, the performance of turbine can be predicted by knowing the specific speed. Okay. Now we will take numerical. Now we will take numerical based on the specific speed. Numerical based on the specific speed. Write down. A turbine is to operate under a head of 25 meter at 200 rpm. The discharge is 9 meter cube per second. If the efficiency is 90%, determine determine first one specific speed of the machine and second one power developed. What is our first step for solving the numerical? First, we will write down all the given data. First, we will write down all the given data. Then, head is equal to 25 meters. Head is equal to 25 meter. Capital N is equal to 200 RPM. Then Q is equal to 9 meter cube per second. Efficiency is equal to 90%. That is equal to 0.90. 0.90. Now, first of all, use the equation that is efficiency is equal to power developed divided by water power, and you can tell the answer in the chat box. Using the relation, overall efficiency is equal to shaft power divided by water power, that is rho GQH divided by 1000. From this equation, you will be able to calculate the value of power. Therefore, power is equal to overall efficiency into rho GQH divided by 1000. Divided by 1000. What is the answer of power? What is the answer of power? That is 1986.5. 1986.5 watt. That is the kilowatt. That is the answer for the power. Now, we have to find out the answer for the specific speed. Ns is equal to N into square root of P h raised to 5 by 4. Now put all the values and the answer will be Ns is equal to 159.46 RPM. Okay, this will be the answer for the specific speed. Okay, today we will end our lecture here. In next lecture we will start our next topic. Thank you.